Uh, Good afternoon, everyone. My name is Rez Mani, and I work for the company ASP Laser Inc. And the title of today's webinar is Nirvascan, Spectrophotometer and its applications. This webinar is being recorded, and the recording will be sent to you after the webinar. My email is also mentioned here. If you have any questions, you can, send me an email and ask me. I know some of you have already purchased the Nirvascan instrument. Some of you have purchased it, but are waiting to receive it, and some others are contemplating purchasing it. So I'm trying to give you as much possible useful information about the instrument and also about the cloud service. So you know what to do when you receive the instrument, or if you already have it, how to use the cloud. So we have a long list here. Actually, we only have about 40 minutes to finish this. There's some time limitation on this platform, so I'll try to mention the important points. I may have to skip some of the points, but I'll talk about the difference between the NearIR and mid-IR spectroscopy, and then the need for a portable NIR spectrometer in the industry. What is the need for this? Then I'll explain the digital light processing methodology or technique versus linear array, and then I'll introduce the different Nirvascan models, the reflectance, transmittance, and fiber optic model. And then we get into some chemometrics, which is the way to analyze the NearIR data. I talk about grapes and analyzing protein and moisture in wheat. And then we have some case studies for the reflective unit in fabrics, plastics, and mosquitoes, for transmittance units, some medical solutions, and crude oil and fiber optic measurement of a spectral profile of a lamp, and also measurement at a distance from wheat. And then if we have time, we look at the app, and we also look at the Nirvascan in literature, scientific literature. So if you look at the spectrum of the electromagnetic radiation, you'll see that the NearIR region from 780 to 2500 nanometer lies right beside the visible region here, which is from 380 to 780 nanometers, and this is part of the infrared spectrum, which also contains the mid-IR and far IR. So mid-IR from 2500 to 25,000 nanometers. So what happens is that when light is shining on a material, there is interaction of light with the material, and due to vibration of molecules, some of these frequencies are absorbed. And you can see here at the bottom there, we have this symmetric stretching, asymmetric stretching, rocking, and scissoring. And these vibrations absorb mid-IR wavelengths. So you can say CO, CH, CN, NH bonds, they absorb mid-IR. So the fundamental absorptions are mid-IR, and that's why there's a good resolution. There are narrow bands, and they're quite strong. However, mid-IR has some issues because you cannot measure watery materials. The water absorption is so strong that it will swamp all the other signals. And there are also some other limitations that I'll talk about later. It's mostly just used for petrochemicals, polymers identification. But if you need an instrument which is fast and quantitative, and it could be used for quality control, you can use a NearIR. A NearIR uses the combination bands and overtones. So you can see here on this diagram, you have the fundamental vibration in the mid-IR. It's about 3 nanomicrons. And then you have the first overtone, second overtone, and third overtone. So these are all the overtones in the NearIR, which we are using. So you can see that the strength of the band or the signal is decreasing progressively as we go to the higher overtones. But the advantage that NearIR brings is that although it is 100 times weaker than mid-IR, it does not require sample preparation, and you can also measure watery materials, and the measurement is fast. So it's very useful for food industry, particularly. Here is some comparison again between the mid-IR. So you see all these spectral bands. There are two peaks, the P and Q peaks for different molecules. They're very well defined and a good resolution. But for the NearIR on the left side, you see it's like a mixture. So there's overtone combination bands, and the resolution is not all that great. So it's sort of combined, many different bonds are combining. So you need to have some method of analyzing this, and that's why we will be talking about chemometrics, because it's not so easy to analyze NearIR because all the bands are overlapping, and the resolution is not that great, and intensity is lower than mid-IR. But still, it's better to use NearIR if you're looking for a fast method of measurement. Here you see the absorption band diagram in NearIR. So we have combination band region, first overtone, second overtone, third overtone. And you see that some of these bonds or some of these absorption bands are common. So CH, CH2, CH3 happen in third overtone, second overtone, and first overtone, and even in combination region. So different instruments of different spectral ranges could work in different overtone regions. And in our case, our Nirvascan instrument, the standard instrument, which is the most popular one, works in the 900 to 1700 nanometer. Then we also have the extended Nirvascan that works in 1350 to 2150. So the standard one works mostly in the second overtone region, whereas the extended works in first overtone region. So the signal strength is higher, but the price of the instrument also is higher due to the choice of detector. And if you have combination band, we have a third instrument that works between 1600 to 2400, so mostly working in the combination band region. And that is we call it the super extended Nirvascan. So let me talk about the DLP method versus linear detector method. So some customers have asked me in the past, so why is that your Nirvascan instrument is cheaper than other type of spectrophotometers? So for example, if you inquire from a company like Ocean Insight, or what it used to be called Ocean Optics before, their spectrophotometers are typically $7,000-8,000. So even up to $10,000. So why is this cheaper? Is this the quality, or what is the idea in here? And one has to understand the different method of processing, which you call the digital light processing. So I'll explain the difference. In the left figure, you see it's a typical spectrophotometer that has the optics. The lamps are shining on the sample, and the light is collimated, and diffraction grating disperses different wavelengths on the detector array. So it uses an InGaAs detector array, and each wavelength is shining on a different pixel. So in case of the DLP method, everything else is the same, but the detector array has been replaced by a micromirror array plus a single detector. So rather than shining everything all at the same time, each mirror, these are tiny mirrors, micro mirrors. They shine towards the, they shine towards the each mirror, and then if the mirror is turned towards the optics, it will receive that particular light. So in this case, you see the green light is turning towards the detector, and after that this mirror would turn away, and then the yellow light would turn, and then the orange, and so on. So the spectrum is built bit by bit, not all at once. So, and this is all happens very fast. This is not like a giant mirror. It's a small, tiny, micron-sized mirror that turns towards the detector, and there is some time that is used for processing the data, basically. So the reason for the instrument being less expensive is that the price of the micromirror array in a single detector is less than the InGaAs array. InGaAs array is quite expensive, so that brings down the price, the cost of the instrument. And also some other advantages to this would be because you have a single point detector, you could increase the size of it, and that would increase your signal to noise ratio. And you can also choose different patterns. If you don't want to, scan from 900 to 1700, you can only say, all right, I'm going to choose only the central section, for example. I would only scan that part. So these are some of the advantages. Of course, there are always disadvantages as well, because, in case of detector array, you can get a live spectrum. You could look at the spectrum in live. It's a matter of like millisecond. You see it's a running spectrum. But in case of the DLP, you need to basically wait for a few seconds, and then it'll take a snapshot of the final spectrum. So these are some of the disadvantages of the DLP as compared to the detector array. Here is a quick optical engine diagram, and you see their lamps at 45 and 135 degree. There's a sapphire window here, and they have the diffraction grating, the DMD board, and the detector. There's also a slit in front of the beam. So here are a few models of Nirvascan these are the standard models from 900 to 1700. So the one on the left side is our most popular unit that we sold tens of, basically, for different industries. It's called the diffuse reflectance model. Then you have the transmittance model, which is used for liquids. This one is only for solids, grains, and powders. This one is for liquids. So basically, you have to pour the liquid in the cuvette, and then the light shines from the lamp into the detector through the cuvette. That will measure the absorbance. Again, here, the fiber model, it does not have any internal lights and can be used with external lights only. So the resolution of all these spectrometers is 10 nanometers, but you'll also get interpolated results at around 3.5 to 4 nanometers when you get the data. Then we have the extended units. So this is 1350 to 2150, and resolution again is about 12 nanometer. You get interpolated values at 6 nanometer, and you can see that this is kind of looks like an OEM model. You can see the circuit here. So what we normally do is that we buy the engine, and then we do a 3D case. We print a 3D case for this spectrometer. So you will not get it just like that with all the circuits exposed. It will be in a 3D casing. So that's our extended model. And as I said, we also have a super extended model from 1600 to 2400 nanometers. That also is available. So once you purchase a unit, we will also give you a link to the PC software that you can download for free. And this is a glimpse of the screen for the PC software. So you will see that there are these tabs here, built-in, previous, new. I need to explain this to those of you who haven't seen the instrument yet. So one, the built-in means for any absorption measurement, you need a reference measurement. So your I over I0, basically, that's the I0 measurement, is a reference. What is the original signal? So this has been already recorded in the factory when the instrument was built, and this is stored in the instrument. So if you put it on built-in, then this button turns into scan, and then you can scan whatever reflected intensity you get. You could just calculate the reflectance and absorbance. But if you decide to do your own reference measurement, you don't want to use the built-in, then you need to put this on new, and this will turn into scan reference. So you would scan reference from a spectral lawn surface, which I'll show you later. It's a highly diffuse reflecting surface. And then after that, you will go to previous, and this will turn into scan. So you do the scan, and this will use the previous measurement of the reference. So you could go at the beginning of the day, do a measurement of your reference, and for the rest of the day, this will be on previous, and it's using that reference measurement for all your absorption measurements. Of course, you need to connect your instrument via a USB to the PC to use this. And these are some of the graphs that you will get. So you have the reflected intensity, which is what is reflected from the material. And then you have reflectance, which is the reflectance function, the ratio of I over I0. I0 is the reference. And absorbance, which is log of 1 over R. And normally for chemometrics and for processing the data, we always use absorbance. So absorbance is what we put in our models as the input. So that's important. So you also have it for transmittance, the same thing. It measures transmitted intensity through the solution, then it calculates transmission function by dividing I over I naught, and then calculates absorbance, A equal to log of 1 over T. Instead of 1 over R, it will be 1 over T. Now, how to record a reference I mentioned, how you want to record a reference. So you can purchase from us this spectral lawn surface. It's a 50 millimeter diameter, 97% diffuse reflectivity surface. So you would put the window of the unit. This is for the reflectance unit, not for the transmittance units. For the reflectance unit, you can put the window directly on top of that, and the software on the new mode here. So you will measure the reference, and then once it goes to the previous, you could measure the actual scan. We also provide the app for this, so it's freely downloadable from either Google Play or App Store, depending on whether you're using the iOS device or Android. And that is it's a glimpse of what the app looks like. And you can also change some parameters using Quick Set in the app. And also, if you look at this PC software, you have the scan config tab here. So normally we use column 1 and Hadamard 1 configs that already exist there, but you can go ahead and create your own scan configuration and then do the reference measurement and use that one. But normally we use column 1 and Hadamard 1. These are the two scan configs. So what is the difference between these? Because the measurement is done in different frames. So you can see in case of the column, so imagine that this is the first frame, second frame, third frame. So first frame, only the first one mirror is turning towards the detector, and the other two are 0. The second one, the second mirror, and the third one. This is only showing 3 of the pixels, not all of them. So only one is turned towards the detector for each frame. But in case of Hadamard, there are multiple. So in the first frame, 1 and 3 are turned towards the detector. In the second frame, the 2 and 3, and in the third frame, 1 and 2, and so on. So you have more throughput in case of Hadamard, which will increase your signal to noise ratio. So a wide DMD pattern is displayed. Higher optical energy will be captured by the in-gas detector. So that's the difference between the two modes. You have a choice to overlay the plots because all the plots are saved or scans are saved in the computer. So if you want to compare them, you put it on overlay and then you can plot all of them and compare them. All right, so let's now talk a little bit about chemometrics. So as I said, you need to analyze the NIR data, and you can't just get away without analyzing it. So whether you're doing quantitative measurements or sorting measurements, you need to use some kind of model. Or in some cases, people use machine learning, but machine learning is usually very useful when you have a large number of data points. For data up to maybe 100, the chemometric analysis would give you better results than machine learning. I know some of our audience are very keen on machine learning and AI, but we have actually compared the chemometrics and AI. In case of smaller number of data points, chemometrics gives better results. So we have for sorting two methods, the principal component analysis and linear discriminant analysis. So basically you do the score plot and each spectrum translates to 1 point in this score plot. So if you are scanning many different spectra, the similar spectra will cluster into one region. This way you can separate different material. Like we do it for plastic recycling. There are 7 types of plastic. So once we do the spectra looks different. And once you do the score plot, they cluster into different regions. And for quantitative analysis, you use the PLS modeling, partial least square. So you need to make a calibration model, and and you should know all the values that was determined by a chemical lab, and then you would make the PLS model and apply it to a validation set. Then you get an accuracy for your model. So here is a very interesting webinar by Dr. Heather Brooks. So we'll send you these links when we send you the recording. I've already given the links to our staff, and he will email you these links. You can watch this. She describes how for wheat, these are some wheat samples, and chemoanalytics has the very important and famous software. It's called Unscrambler that could analyze. It has many features, and it could analyze and do the modeling there. But unfortunately, the software is quite expensive. So something like probably $10,000 or so if you want to get it only for 1 year. If it is 3-year deal, it's like $5,000. So not everyone can use this. But the idea I want to show you here is that this is the way you have to organize the data. So all the absorbances at different wavelengths will be around horizontal rows. So here you see these are the wavelengths, and this is the first spectrum, second spectrum, third spectrum, and so on. And this is looking at protein in wheat, and this is the percent of protein in wheat that should be put in the first column. So this is how you organize the data, and we also do it similarly in our cloud platform, which I will describe later. So let's get to some case studies. So our first chemometrics study was on using a data that was given to us by one of our clients in France, and he works with grapes that are used for making wine. And he wanted to model the Brix content or the sugar content of these grapes. So he actually sent us this spectra, about 53 spectra for the calibration. And we also measured the Brix content using the Brix Meter, which is using a refraction method. It could determine accurately what the Brix content is. So the ground truth basically was the Brix Meter values. And these are the spectra. And right off the bat, you can see by visual inspection, this is an outlier. So, it's good to visually first inspect and remove the outliers from the set of a spectra. There are also methods in chemometrics to determine what the outliers are, but some of them are very obvious, like this one, which I have already removed. Now, the thing is that if you look at the spectra, you see there is a DC offset between different spectra. And this is quite normal in case of NearIR. There's a large scattering and causes a DC offset. You may even measure from the same sample at the same spot 3-4 times, and you see that there's a DC offset. So they're vertically displaced. They should look similar, but the spectra are vertically displaced. So in order to get rid of that for the PLS modeling, it's very normal to use the second derivative. So you differentiate twice, and that will get rid of the DC offset. And the peak that you see here for the second derivative is at the same position as the original peak. But the downside is once you do the second derivative, it introduces some noise. So to get rid of the noise, we have to apply the Savitzky-Golay filter, which has a certain width, and it basically fits a polynomial into this region. So rather than having this zigzag pattern, you have a smooth curve, and that will be the Savitzky-Golay filter. So here's the example. So I already showed you what the raw spectrum looked like. This is the second derivative and the Savitzky-Golay applied to it. And then we made this PLS model, calculated versus actual response. I mean, some calibration points were missing at the center. It was not the best calibration set, but I used the software Minitab to do the fitting, and here is the values, the real values, the predicted values, and we got a RMSE, root mean square error of 0.77 Brix, which was not bad for our first attempt. Okay, our next serious project was the wheat project, so measuring protein and moisture in wheat. So we have a collaborator in Manitoba that deals with a lot of farmers, and the farmers, they want to know what the protein content of their harvested wheat is. So first of all, why they want to know that? Because the price of the wheat is directly proportional to the protein content. So the higher the protein content, the higher will be the price, as this curve shows. There are several ground truth methods there to measure the exact value of protein. So the HPLC, high performance liquid chromatography, is very common. You have the Kajal-Dahal method, the Dumas combustion method, and our customer had this very expensive $20,000 grating monochromator instrument. So you would just put the wheat there in the chamber, and it will just use a grating monochromator and analyze the spectra. And it will give you a slip of paper with the protein and moisture content on it. But the idea is that would we be able to do that with a $2,000 instrument by doing the modeling? So he provided us several basically samples to do the PLS modeling. And that's what we did. So all the values, all the samples, they were measured with their ground truth instrument. And we did 4 measurements with the spectrometer, with the reflective model. There were 100 samples in total, so we divided them into 80 calibration and 20 validation. Usually the ratio is 4 to 1, or 20%, 80%. And then we did the second derivative and Savitzky-Golay. And then finally we came up with this PLS model that gave us a RMSE of 0.47%. So these are predicted models, predicted versus the real. So the line shows the real, and these are the predictions. So he had actually originally given us a larger range, 12.6 to 19.1, but we only used this central region because we had enough samples to do the modeling. In other regions, we did not get a good results because there were not enough samples. And it was hard to get these samples in other regions. Similarly, we did moisture. Moisture is important because it affects the storage conditions for wheat. So higher the moisture, higher is it's more difficult to store the wheat. And we got similar type of measurements and modeling, and we got a RMSE of 0.34%. All right, so I'm going to spend probably about 10 minutes talking about the cloud service. So quickly doing a demonstration of the cloud service and what is important. So our cloud service is capable of, you could upload your spectra and profiles, and you can do pre-processing, and then you could do a modeling and much more. So let me start the NearIR Cloud. So NearIR Sorry, there's a typo here. NearIR Just give it a second. Just a minute. NearIR So let me actually try it on a different platform. And if sometimes the cloud is down, but let me try if this one would work. If not, then. Okay, it's like this is not, this is momentarily down. I have to talk to our system administrator for this, but it's okay. I can explain here. So basically the NearIR Cloud, what I'll do is I'll add another a YouTube video of the NearIR Cloud demonstration. I'll send you so you can take a look at it. So you see, once you get into the NearIR Cloud, you have to register, and you enter into the NearIR Cloud environment. You have this menu on the left side. All right. So you have a spectra. You can choose and upload the spectra and make profiles, like a combination of different spectra. Let's say you measured from, you had 100 samples of wheat, and they could all be in the wheat profile. And then you can also do pre-processing. So what I was telling you about the Savitsky-Golay and second derivative, you can do it in the NearIR Cloud. And also you can make the PLS model and PCA model, LDA model for sorting. So these are all options that you have there. Now, another very interesting feature that we added to this, if you go in the NearIR Cloud, you see there are two buttons here at the bottom, which you don't see right now in this screenshot, but one is called the averaging and the other is called the interpolation. So the averaging is that if you do basically 4 averages from, like, for each sample, you do 4 averages. So in your data file, there's an absorption column. So you could just select all those, and it will just do the averaging for you. You don't have to just grab it from there and extract it and do the manual averaging. So the averaging button will also do the averaging for you and extract everything. And then you have the interpolation button, which is another important one. So I'll explain that a little bit later. So here is like an example of PLS model for wheat that we made on the cloud, and then also the LDA model for sorting plastics that we could make on the cloud. So let me talk about the interpolation. So the need for interpolation, which you basically feed that and feed it to the this button. When you press it, it will ask you for the file, and then you would it will give you the interpolated values. So let me explain what that is all about. There's only 4 minutes remaining, so I'll have to do quickly on this one. So it's better to do the interpolation, because if you don't do the interpolation, the wavelengths will all be different. So here you see first the spectrometer 901.81, this is 901.56. So these scales are all different. So you need to uniform scale, and then you also need to use the sampling theorem, and that will be half the interval. So normally it's about 4 nanometer difference. So half of that would be 2 nanometers. So all your spectrometers will be having the same wavelength scale there. And, this will remove this variance in case of the wavelength. So it's quite important. You can also do slope and bias corrections, because if you do the model with one spectrometer and then you do the measurement with the other, there are some differences. So you need to have this bias and slope corrections to make them similar to each other. So there are several applications here. For example, we don't have time to go through all of them. The polyester content in case of fabrics, for masks, for plastic sorting, we did very good models, LDA models. And here, some of our clients are using for Zika virus, for malaria, Zika virus, and flu, they're using it. The transmittance measurement is useful for that. Here's the transmittance instrument that you can see here. And we did oil measurements. And this is the fiber optic unit. And in the fiber optic unit, you need to connect some kind of device like a reflection probe and measure from the calibration source first, and then from the actual sample. There's also a video that I'll send you. This uses another lamp called DRP1 that measures from the wheat remotely without touching it. So the YouTube video will explain that. This is this app, and some scientific Nirvascan in scientific literature if you want to see like some papers that talk about use of Nirvascan. So in conclusion, the Nirvascan instrument is quite useful in many industry and applications. Unfortunately, we don't have enough time to continue this due to time limitations. I do apologize for this limitation, and hopefully we'll do a better job in our next webinar. Thank you very much, and have a good day.